Welcome everyone. Thank you for joining us. This is Gabe Arnold with the DLC, and you are attending a webinar on Advanced Lighting Control System Performance, a field evaluation of 5 systems. These were 5 projects that were installed mostly in 2016 and 1 project in early 2017. And what we'd like to do is share with you what we learned from these projects. Let's quickly go over some webinar logistics. First of all, the question we most often get is, will DLC provide access to the slides in the webinar? And the answer to that is yes. Both the slides presented today as well as the recorded webinar will be posted to the DLC website following the presentation. We have a section on our website specifically for webinars. It should be pretty easy to find, so that's where you would go to find this following the presentation today. We have a lot of people on the line here today, so everyone will remain on mute through the duration of the call. We do ask you to ask us questions. What we're going to do with this webinar is we won't have time for a live Q&A session, but what we will do is follow up with attendees with answers to questions that were received during the webinar. So please do make sure you ask us your questions, and we'll be sure to follow up with you afterwards. If you do experience any technical issues as you go, please let us know. We have someone monitoring both the chat pane of the GoToWebinar interface as well as the question pane of the GoToWebinar interface. So let us know if you have any troubles, and hopefully we can respond and address them as we go. I'd like to introduce our speakers. First will be myself. My name is Gabe Arnold, and I'm the Technical Director for DLC, where I'm responsible for DLC's technical strategy and development of our resources for our solid-state lighting and network lighting controls program. This includes our minimum specifications and associated qualified products list, as well as some of the tools and trainings that we've created to advance the adoption of network lighting controls and solid-state lighting, along with research reports such as you will hear about today. I've been at the DLC for about 4 years as a direct employee, but involved since the DLC got started with qualifying LED products back in 2008. My career has included roles as a lighting designer, a utility program implementer, a consultant, and now with the DLC. I am a registered professional engineer and lighting certified by the NCQLP. I'll be presenting the introduction here and the lesson learned. The other speaker is Michael Meyer with Pacific Northwest National Laboratory. Pacific Northwest National Laboratory partnered with the DLC on these projects. I'll talk a little bit more about that. They did a lot of the technical evaluation and analysis and authored the report and case studies. So Michael is going to be representing their work. He's actually pinch hitting here for Eric Richmond. Some people on the line may know Eric. He was the lead on behalf of PNNL for these projects. He's since retired, so Michael is stepping in to present these out. So thank you, Michael. An introduction to Michael. He's been with Pacific Northwest National Laboratory for over 10 years. Prior to joining the lab, he worked as an architectural lighting designer. Currently, he splits his time between 3 major programs, the Commercial Building Integration Program, Codes and Standards, and Solid-State Lighting Commercialization. Michael's been involved in many field evaluations and demonstrations across the country with many lighting technologies and different applications, and he's authored a whole lot of very useful reports. He's got a master's in lighting degree from the Lighting Research Center at RPI. So thank you, Michael, for your time. The agenda, pretty straightforward. We're going to start here with an introduction and some background to all these projects. Then Michael is going to talk us through some of the findings, and then I will conclude by talking through some of the lessons learned. So let's dive in. I want to thank the funders that provided the funding to make these projects happen. These demonstration projects were enabled by a grant from the US DOE and co-funded by a group of utilities that you see on the screen. This included National Grid in Massachusetts and Rhode Island, Eversource in Massachusetts and Connecticut, United Illuminating in Connecticut, and the state brand for the Connecticut energy efficiency programs called Energize Connecticut. We couldn't have done these projects without their support, and both in funding and participation. Many of these demonstration host sites were found by some of these partner utilities, so we're very grateful for their support. I also want to thank all of the project participants. If you've ever done one of these projects, or really any construction project, but maybe more so a demonstration project like this where there's a lot of evaluation, it does take a village. And we want to thank the installers, the specifiers, the manufacturers and representatives, and especially the site hosts for their participation and support on these projects. MJ Fish LLC, Ahold Corporation with their Stop and Shop stores in New England, the Rhode Island Public Utilities Commission, Two Roads Brewing Company, and Yale University. These are not typical projects and they require a lot of extra effort, and we're grateful for the participation of all involved. We had 5 objectives in implementing these demonstration projects. First, we were looking to demonstrate new and promising advanced lighting control technology. We wanted to create a suite of case study example projects that we could use to encourage others to adopt this technology. Second, we were looking to gather more data on how much energy these advanced lighting control systems can save. Our stakeholders, including utilities, specifiers, and end users, have communicated that they're looking for more data and certainty of how much energy advanced lighting controls can save. Third, we were looking to understand what was the experience in installing these systems. All of the systems we demonstrated, including new innovations designed to improve the installation experience, to make things simpler. We wanted to see how this went. Fourth, we were looking to understand the impacts to occupants of these new systems. If these systems save energy but have negative impacts on building occupants, that's something that's got to be addressed. Finally, based on all that we learned, we were looking to identify barriers and opportunities to technology adoption that we can work on. At the outset here, we'd like to note that these projects were not deep dive research projects. We had limited time and funding, and we're looking to assess the objectives that I just went over at more of a snapshot level. In assessing the energy savings, we did not do exhaustive pre and post metering of the entire facility. Rather, we metered a subset of lighting we selected to be representative of the overall project. We metered this lighting generally for 2 to 4 weeks pre-installation and 2 to 4 weeks post-installation. We then extrapolated these results across the facility and across a year. In a deep dive research project, you'd want to go a lot deeper on this, do a lot more pre and post metering, and probably meter more of the facility. That's not what we were looking to do here. That's not what our budget and time allowed us to do. So this is more of a snapshot, and that's something to keep in mind as you're reviewing the results. In assessing the occupant satisfaction, it was a similar, more of a snapshot approach. We had the building occupants complete a basic survey pre and post installation, and we evaluated the results of that survey pre and post. And to assess the installation experience, we had installation contractors similarly complete a written survey to tell us how it went. You can find more information about the methodology in the report that's posted to the website. Let's talk about the technologies that were demonstrated. The technologies were selected via an RFQ process back in late 2015. Manufacturers submitted proposals to us and were scored by a team of non-industry, due to conflict of interest concerns, subject matter experts, They were from utilities, from national laboratories, DOE, the General Services Administration. We tried to gather up all the experts we could find that weren't actually working for a manufacturer. The scoring criteria for selecting the technologies was specifically weighted to technologies that used innovative approaches to overcome technology adoption barriers, cost, complexity, ease of install, things like that. And on the left side of the screen, you can see the top 9 systems that were selected. Once we had these 9 systems, we then went out to find host sites for the technologies. Easier said than done, I'll say. More about that in a minute. I think it's useful to understand what the scoring team saw as innovations to address the technology adoption barriers, what they scored highly in selecting these systems to demonstrate. First, many were interested in embedded or integrated controls and sensors that were integrated into the luminaires, pre-installed in the luminaires, also known as luminaire level lighting controls, or LLCs. They saw benefits of having the controls pre-installed in luminaires, potentially saving in installation costs and addressing compatibility issues of matching luminaires controls to controls after the fact or on site. Secondly, they saw benefits to wireless systems and eliminating the costs and challenges of control wiring. They were looking for systems that were open standards based or interoperable as possible. That was another feature. And it's for the additional benefits they can provide in connecting to other building systems and increasing the value proposition for advanced control technology. In addition, they were looking for systems with a distributed intelligence architecture, where the intelligence is distributed to the devices and not reliant on a central gateway or server in order for the system to run, as this may provide more scalability, resilience, and reliability for the system. Next, embedded energy meters were also scored favorably for the enhanced value proposition that the energy data can provide for these systems, along with the potential for eliminating the need to manually input wattage and dimming curves into advanced control software to understand energy savings. This is a new innovation, incorporating these metering chips directly into drivers and devices that has these benefits versus the older methods, which required a commissioning agent or installer to actually choose the wattage of the fixture that's being controlled and maybe make assumptions around the dimming curve in order to estimate energy savings. Finally, the scorers were looking for systems with well-executed interfaces and simple commissioning. As we know, historically, the complexity of these systems has contributed to higher costs and slower adoption. Out of the 9 technologies that were selected, we ended up with 5. It was a challenge to find host sites, maybe not surprising, but there was a lot of additional participation required to support these projects by host sites, a strict timeline, which unfortunately didn't fit into the decision-making process of some of the host sites that we talked to, and the systems were not offered for free, and that was by intent. We really wanted the host sites to have some skin in the game, and so they did contribute some towards the cost of these projects. So in the end, we found 5 host sites. First was Two Roads Brewing Company in Stratford, Connecticut, who installed the digital lumen system. Then Rhode Island Public Utilities Commission in Warwick, Rhode Island, installing the Philips SpaceWise system. A multi-tenant medical office building in Avon, Connecticut, installed the Cree SmartCast system. A super Stop and Shop grocery store in New Bedford, Massachusetts, installed the Daintree from GE Current system. And finally, Yale University in New Haven, Connecticut, installed the Enlighted system. I'd like to give you a little bit more information about each site and technology, and then Michael will take us through some of the findings. Our first site was Two Roads Brewing Company in Stratford, Connecticut. This was a large brick industrial building that was renovated in 2012 to hold Two Roads Brewing Company. This is an industrial scale brewing operation with bottling and brewing operations a warehouse, shipping and receiving, a large bar, tasting room, as well as retail space, and corporate offices for the company. The facility was about 100,000 square feet. This was an exciting project that went quite well. It was also our favorite site visit because the beer here was actually quite delicious. One interesting thing about this retrofit of lighting is that we replaced lighting in the facility that was only 3 years old, and what had been at the time state-of-the-art and most efficient high-performance T8 lighting. I think this illustrates just how quickly the LED opportunity came along and that we were able to cost-effectively replace lighting that was only 3 years old. The technology installed at Two Roads was the Digital Lumens Intelligent Lighting System. This system was a combined integrated system, meaning that the controls, sensors, and luminaires were one. They were a package, integrated with one another. If you look at the fixtures on the slide, the second fixture from the top is the Digital Lumens High Bay fixture that was installed in high bay areas. You can see that it incorporates a built-in occupancy and daylight sensor into the luminaire. Below that is an integrated sensor module that Digital Lumens offers that allows the system to be integrated into other manufacturers' luminaires. In this case, the sensor was integrated into a Philips troffer and shipped pre-installed to the job site to be installed in office areas. The bottom fixture there was used in low bay areas of the manufacturing space. This Digital Lumen system communicates through a wireless network, so no control wiring is required. Existing luminaires can be replaced one for one and controlled intelligently without the need for any new wiring, no control wiring. The wireless network connects to a gateway and a computer server that houses the system operation and configuration software. The system provides the ability to do remote monitoring and control, as well as supporting a growing range of IoT applications using data provided by the system. We have a few photos of the site here. I would like to note here, maybe at the beginning, that we had some technical difficulties in finding all of our photos, so I apologize, but some of the photos here of the sites are lacking. We might have liked to show you more pre and post photos, but we don't have that. So you can see on the lower right, the site included some large high bay spaces for the brewing operations with some opportunities for daylight that you can see in the upper left there with some windows. The lower left is some of the low bay space for bottling operations. Upper left is some of the office space. And in the middle there is, if you're in the Northeast, an iconic, hard to find beer called Sip of Sunshine, and all of us were sort of drooling, never having seen pallets full of it. It's usually something you have to wait in line an hour for to get. So that was fun. This next slide is showing some screenshots of the Digital Lumens Light Rules software. During a post-installation site visit, they showed us how they were using this software. On the lower left is a photo of the scheduling interface, which is really more like an Outlook calendar that enabled them to easily set different schedules for different areas of the facility. This was something they were not able to do with their prior, or not easily do with their prior lighting control panel. On the right side of the screen is a reporting feature of the Digital Lumen software that uses the occupancy sensing data from each fixture to create heat maps of building occupancy. They weren't using this information to make any changes to their actions in the facility at the time of our site visit. I don't know if they are at this point, but this type of information can be used to optimize space utilization along with their building and manufacturing operations. On the upper left is a screenshot, actually grabbed online, not from on site, but it was something they showed us on site that we didn't get a picture of a capability provided by this Digital Lumen system to automatically test battery backup emergency lighting and produce a testing report for OSHA emergency lighting testing compliance. This was something the brewery was pretty excited about. This previously required a manual process, walking around the entire facility to test each luminaire and produce a report for OSHA compliance. With this new system, they can produce a report at the touch of a button. Our next site is the Rhode Island Public Utilities Commission. This is a 3-story building that houses the state's regulatory body with responsibility for oversight of the state's utilities and communication entities. In many ways, this was like a typical office building with private and open offices, conference rooms, and corridors. However, in addition, it also included a large hearing room for regulatory proceedings that was more like use cases for auditoriums or presentation spaces that were able to benefit from the flexible control provided by the advanced control system. Like the last project, this one involved replacement of T8 lighting, and some of the spaces here actually already had occupancy sensors, which we'll talk more about. The technology installed at this site was the Philips SpaceWise system. This network system utilizes a mesh-based wireless network with embedded sensors and controllers pre-installed and pre-shipped in each luminaire. You can see the sensors in the photos. There are also optional wireless switches available to provide local control of the lighting. Unlike the last system, this one does not utilize a gateway or server. The network is fully contained within the onboard sensors and controllers. And this is it's a simplified network system really designed to provide most of the energy saving and advanced lighting control features of a network system in a easy to install and configure package that does not require a computer server. The lighting for this system is configured using a remote control. You can see some photos of the site here. I think the one thing I'd like to highlight is the lower left, the photo of the wireless switch, hearing room A. So what they did here is they took some of those wireless switches for the system. You don't actually have to install them on the wall. You can actually install them as a free-floating device and put on a desk. And so they had a few of these up near the commissioner's and hearing officer's desk that allowed them to control the lighting in different areas of the room to support different needs in the space for presentations or hearings or so forth. The third site was a multi-tenant medical office building in Avon, Connecticut. It included 8 different tenants. So we were installing this new lighting in 8 different spaces with 8 different customers, all with a single building owner, which is very common out there, but definitely brings up some unique challenges. In this case, all these tenants were in the healthcare space. We had tenants that provided primary healthcare, dental, optometry, eye care, physical therapy, and psychiatry. The spaces included your typical office type spaces, private offices, open offices, and conference rooms, as well as some healthcare specific rooms, exam rooms, dental procedure rooms, and even workout rooms for the physical therapy tenant. As with the prior projects, the existing technology here was T8, and some spaces had occupancy sensors. The technology installed at this site was the Cree SmartCast wireless system. This system is in many ways similar to the previous Philips SpaceWise from the last project. It utilized a mesh-based wireless communication network with embedded sensors and controllers, pre-installed and shipped in each luminaire. They also have optional wireless switches available to provide local control. And like the SpaceWise, it doesn't include a gateway or server. It's fully contained within the onboard sensors and controllers. It's also a simplified system designed to provide most of the benefits of an advanced lighting control system or a network system and an easy to install and configure package. We were not able to locate the photos for this project, so I'm showing you the best we were able to find in the files, and this is a floor plan of one of the floors. One thing to point out here is you can see the large number of small spaces. These were the small offices and exam rooms. And we'll talk about some of the challenges we encountered there around occupancy sensors. The fourth site was a super stop and shop located in New Bedford, Massachusetts. This is your typical full service grocery, over 70,000 square feet. Included a large retail space and some back of the house spaces for offices, shipping and receiving and storage. Existing lighting at this location was T8, and there were no existing controls beyond some very basic scheduling controls. The technology installed at this site was the Daintree Enterprise Wireless System by GE Current. This system utilizes an open standard-based, the only system that uses an open standard-based protocol, Zigbee-based communication protocol. It does utilize a gateway and a server that houses the operation and configuration software. Although at the time of this installation, embedded sensors were not offered by the manufacturer. They are available now. However, so we didn't pre-install sensors with this one. We installed more traditional remote mounted sensors. However, the system does utilize these wireless network controllers that are installed in each luminaire. And we did have these pre-installed and pre-shipped. Pre-installed by the luminaire manufacturer, which was Eaton in this case, and pre-shipped to the job site so that on-site installation of these controllers was not required. The Daintree system has the ability to scale up to an enterprise level system, enabling control and monitoring of multiple facilities, along with support for a growing number of IoT applications. Here's some photos of that site. This was a traditional grocery. And then finally, our fifth site was the Human Resources Administration building at Yale University in New Haven, Connecticut. New lighting was installed on the 5th and 6th floors of this building, representing about 25,000 square feet. This was very typical office space, including private offices, open offices, conference rooms, and corridors. As with all the projects, the existing lighting here was fluorescent T8, and there were some existing occupancy sensor controls. So that's an overview of, oh, sorry, I need to talk about the technology. So the technology installed at Yale was the Enlighted system. So this system utilizes a network of small embedded wireless sensors within each luminaire. And so you can see a photo there on the left of the size of that sensor. And what this does is each sensor within the luminaire, along with control, enables advanced control of the lighting and also IoT applications that are enabled by data collected by the system. As with the other projects, the sensors were pre-installed within the luminaires to simplify the installation. This system utilized a gateway and computer server that housed the operation and configuration software. The software includes a pretty sophisticated energy manager application that also includes a number of analysis tools to support IoT use cases, such as tools to optimize space utilization. So you can see examples of that in the graphic. So that's an overview of the sites and technologies. So I'm going to pass things off to Michael here to take us through the findings. Okay, Michael, you should be set.
Okay. Hi, I am Michael Meyer. As Gabe introduced, I'm with Pacific Northwest National Laboratory, and I did step into this, so I will answer as many questions as I can, as well as present on the report and the information previously provided. Okay, oh, there we go, perfect. So moving into findings. This chart is a comparison of all five, it's the average of all five projects. Obviously, we converted first from fluorescent and a handful of places HID to LED, and then you layered on the advanced lighting control systems. The majority of the rest of the presentation will focus on the controls. So I just want to touch base here. Obviously, the large bulk of the savings came from first converting from fluorescent to LEDs, as shown in the green piece. Then the blue and light blue and orange represent what the controls did. Now, this is an aggregate average for all five sites. These energy savings were only from lighting. There was no interfacing with the HVAC system or plug loads. The controls did interface with other features, such as non-energy features like testing and the mapping that Gabe showed earlier. But all data presented going forward will be energy savings only from lighting and not monetizing any other type of data point. And so first, always good to touch base on some lighting controls, make sure everyone knows some terms. The paper to the right is from 2012. It's the lighting controls in commercial buildings. It's a large meta-analysis. It's a great resource. I go to it often. I do mention that it was published in 2012. I don't think controls change that frequently. That being said, I think as we see more LED projects come online, we might see more use of controls and hopefully some greater resolution in those data points. I've said it before, but I'll start trying to provide some definitions now. The first is high output trim, also known as task tuning. The concept here is that your fixture is shipped with a full output setting, obviously. And the idea is that in the field, either through a mechanical, maybe a dip switch, or in this case, possibly some type of remote setting, you're able to reduce the output, not from a full output to say 70% output or 65% output. This can be done based on needs for meeting the IS light levels or personal comfort. The controls analysis suggests that on average, you're seeing about a 31% savings from personal tuning and 36% savings. Now that's an average from the paper. The occupancy-based, obviously, is using a sensor to modulate the light output based on occupancy or movement. This is highly dependent on the type of space you have. It is 24% energy savings is the average from the report. Now, it matters if you're in a bathroom versus an office setting. Obviously, bathrooms have less scheduled use, and therefore occupancy sensors save more. Obviously, if you're in a space, let's say a call center versus a dedicated office where you might have people traveling or other out-of-office needs, occupancy sensors save different amounts. So it's important to know your space considerations before you assume what these control savings will be. Finally is daylight harvesting. The concept here is if you have an opening in the wall or in the ceiling, you can bring in some daylighting and you can reduce the electric lighting in response to the available daylighting. Again, highly dependent on a handful of variables, and it typically saves about 28% energy savings as well. Continuing on. So we saw about a total of 40% energy savings when you only looked at the controls. So the concept here is if you've already moved to a new technology baseline, and you only analyze what did the controls provide as an energy savings, it was 40% compared to that baseline. The three different colors give you a representation of how that 40% was developed, with tuning representing about 50% of the total energy savings, about half of the total energy savings, with occupancy sensors being the next dominant amount of energy savings, and then finally daylight. As you can tell by the two bands there, both daylight and occupancy sensors provided roughly the same amount of energy savings. It's a good time to note that, as I showed in the previous report, slide, that energy savings from tuning typically is in the mid 30% centile. We are seeing with new LED fixtures that some manufacturers are shipping one fixture and sites are tuning them significantly. So in some cases, a fluorescent system might have drawn 30 or 35 watts, but it's being replaced with a 40 or 42 watt LED fixture, possibly for SKU control and other management issues on the manufacturer side, or the contractor doesn't want to have to manage which fixtures go where, and then they just are going to tune them in the space. So in some cases, we've seen some artificial tuning numbers that are maybe 60 or 80%. At that point, it's probably that the new fixture installed was over capacity, but there was other reasons for it. So tuning is a number you need to pay attention to. If you see a large, significant number from energy savings from tuning, it might be possibly that the original fixture may not have been sized properly. But we'll touch base on that a little more. Sharing some of the results. So as Gabe mentioned, there was a brewery. You can the table here is the luminance values. This site did not have any tuning. However, you'll notice that they probably could have benefited from some. Most of their post-retrofit light levels are actually increases. There probably could have benefited from that. There are some highlight levels. 56-foot candles in a waiting lounge is a pretty bright waiting lounge. Same with a lunchroom. Had they used tuning, they probably would have reduced those levels and seen some additional energy savings. Moving into the next site, this was the office setting. This was the Rhode Island Public Utility Center. This is they soon tuned to about 12% energy savings. This was factory tuned at the fixture manufacturers. They had a roughly about corresponding reduction in illuminance. Notice how it's kind of balanced out to what we would see for IS recommendations for lobbies and hallways, and they probably could have reduced a little more, but it all depends on what the occupant preference is and other features. Continuing on, the medical office, as Gabe mentioned, this was a multi-tenant medical office, which complicated the demonstration, obviously. The other challenge here was the site originally resisted some of the activating certain levels of controls. They went first with occupancy sensors and didn't activate the daylighting and some of the tuning features, even though they were already installed on fixtures. It wasn't upon a second trip back to the site did they activate those features. As a result, some of the energy savings directly attributable to tunings were not directly clear, and so it's a little bit of a muddy number, but we do think it's possibly 6% or higher. The occupancy sensor was very significant, so it's hard to tease out some of those numbers. Notice how they went from 63-foot candles in the suite 304 to about 25-foot candles in the new LED design. Obviously, pay attention to your pre-design when possible. What are the existing conditions? Are they overlighted? That's a great recipe for energy savings on the tuning side. Previously in the 80s and 90s, we were overlighting offices previously for less computer-based work. Computer screens are now common in every office, as well as the monitors are just better, and therefore we don't need as much light, and some of those challenges have changed. Pay attention to what the IS recommendations are, because it helps inform what some of your new tuning levels could be. Continuing on into retail grocery, this is a grocery store. Notice how they changed some of their light levels. They balanced out the central storage and the cracker and juice aisle. Pretty much 15% reduction in illuminance is very similar to what they saw in the pre and the post, so they were really matching what their preference for it was. But notice how the change they saw in the floral shop, going from 64-foot candles to about 33-foot candles. Again, tuning allows you to really not have to accept one light output for the entire space, and you can dial it in. In a retail application, it's a great example of you may want less light in a floral shop, either to just make things stand out or to draw people different places in the store. Finally, we end up with the office at Yale University. Notice they have about a 43% energy savings. Again, this is a classic example of a meeting room being overlighted. I think most people now would be very scared of going into a 62-foot candle meeting room. We'd probably not want to spend a long amount of time in there. 45 is more typical to what we are seeing for design recommendations, even with some video conferencing aspects. Moving beyond tuning and light levels, as Gabe mentioned, we had some occupancy sensors. Two of the sites had previously had occupancy sensors installed. They happen to be both offices. Those are shown in red because they actually resulted in negative energy savings when we went to the new digital advanced lighting control system. There are some different philosophies on why we think this negative savings occurred. In the previous installations, they were going from straight on, off. In the newer settings, they were going from on to low output to another time delay, then finally off. So that is reducing some of your energy savings. Also, there's a difference in sensitivity features in the difference between the two controls, and the digital ones might be more sensitive. So it's something to pay attention to as you migrate to newer controls. They may not behave the same way you previously thought, and you may result in possibly, in some cases, negative savings as possible. Retail, it's not surprising to have a low occupancy energy savings. It's becoming more common to see that, especially in the grocery area, occupancy sensors in the display case area, but the rest of the store, it's pretty uncommon to see occupancy sensors in a grocery store in the general aisles, and especially in the non-grocery stores in a clothing or home improvement store, we're not seeing it really occupancy sensors deployed anywhere in those type of spaces. Continuing on to daylight savings, we saw a pretty good consistent range between 6 and about 16% energy savings from the daylighting. The biggest challenge with daylight energy savings is architecture. As much as you might think you're going to get energy savings from daylight sensors, it's really all dependent on your building. Do you have cubicles? How high are they? What the reflectances are? What other design features do you have? Those affect daylight savings more than the lighting control system selected or the light fixtures. So very much pay attention to your space and don't assume certain levels of daylight savings will be available. Moving into some of the cost effectiveness of this, a typical lighting installation is about $4 a square foot. That's a general rule of thumb. Don't hold me to that if your project comes in differently. But you'll notice that two of the projects came in much higher, one at $7.99 a square foot, and the other is $5.72 a square foot. Those were actually more affected by the fixture selection, not the lighting controls. They were not what was pushing them over. In those cases, different appearance of fixtures affected those prices more than the lighting controls. So again, it's your fixture selection can affect your overall cost, not the controls that may be putting it over. But also notice the rebates on the comparison of two slides. Rebates are very helpful. In some cases, it reduced the project cost by almost 50%. They are still needed and can help make or break a project. As I mentioned earlier, there's a range in cost per square foot, and here now we're trying to graphically kind of show what some of those fixtures are. The standard troffer, the ones on the left, are pretty common. We all have a bulk price in our mind of what those cost. The one in the center, that was a much higher cost per square foot. It's a linear pendant system. The price on the fixture for either appearance or installation or other needs affected it more than the other fixture cost. You'll notice also over on the right, at the 100,000 square foot, it was a mixture of a high bay and a troffer. Again, this is a situation where the high bay fixtures had a greater fixture density, so you could space more fixtures over more fewer fixtures over more area, and thereby actually dropped its cost per square foot down. So sometimes when you hear a ballpark price of $1 per square foot, you need to make sure, well, am I comparing the right comparisons, both fixture type and application? An office should have one price versus maybe an industrial where you're going to have fixtures mounted higher and thus farther apart. So pay attention and not just compare directly numbers. Continuing on, we saw a wide variety in terms of payback as well as saving to investment ratios. SIR is saving to investment ratio, and if you're not familiar with that, the idea is over the life of the system, in this case it was assumed 20 years, will the system pay for itself? You want the SIR to at least equal 1, so it's paid for itself in 20 years, and the higher the SIR, basically the faster it pays for itself. Again, rebates played a role. You'll notice that as Gabe mentioned, the brewery was previously had been upgraded not only 3 years ago with a fluorescent technology. That's one of the reasons why the simple payback is without rebate is over 11 years. If you're comparing against a relatively efficient baseline, that can affect the cost effectiveness of your new installation. Similarly, for site number 2, the office, that was already a very efficient operational scenario as well as low operating hours. That's why the annual energy savings are much lower than all the other sites, which affects both its payback and some of the other features. So again, they all play a role. Moving into 3 specific sites, we actually had rather detailed cost data, so we were able to show this slide. The upper top row is $5.72 a square foot. That was the total material and labor cost. Then you can subdivide it by both fixture and controls. You see that in this case, installing these fixtures cost about $4.24. That was material, and $1 a square foot for labor. Controls material was about 29 cents a square foot, and labor, I'm sorry, I got those backwards. Labor was 0.29 cents, 29 cents a square foot, and the controls were about 15 cents a square foot for material. So in this case, the cost, if you only examine the cost. It was about $8,000 for the total controls. However, the controls only saved about $200 a year, resulting in a 45-year simple payback. Though I would say don't be scared by that 45-year payback. The cost, the actual absolute cost, was so low compared to the overall project. It's helpful just to kind of include it on the project because it's not going to really push you over. Also, in this case, had the occupancy sensors not been in the baseline, you probably would have increased your energy savings and therefore not had the negative value and been able to claw back and make your economics a little better in this scenario. Similarly, for Office 3, this is again, you had $3 a square foot. It was about $2.80 a square foot for the fixture and labor combined. We didn't have it subdivided, but we just know that the fixture and labor was materials were $2.80 a square foot. Similarly, the controls, labor and materials were about 23 cents a square foot. Here, because of different operational characteristics, the lighting controls are saving about $4,000 a year, and the total cost only was about $6,000 a year. As a result, we had a 1.5-year simple payback. In this case, the energy savings were significantly being driven by the occupancy sensors compared to the other type of controls. So the low first cost helped. And probably the occupancy sensors in a multi-tenant space were probably more effective than the tuning. Finally, moving into the retail grocery site, you've seen this before, about $7.99 a square foot for the total project. Here, both the labor and materials for the fixtures is really what drove the price there. Almost a whole $6.50 was directly related to that. The controls, material, and labor were really only about $1.40. As a result, the controls saved at more energy than the actual equipment fixture change did. So in this case, the lighting controls are saving almost $36,000 versus the $30,000 from the fixtures. Yes, the controls did add $108,000 to the total overall project, but they had a 3-year simple payback. So it's important to separate these numbers out, especially if you're adding on and not thinking about that the controls are what's driving over the project versus the fixture costs. This slide, there's a lot to pack into it. On the left-hand column, it's your controls, materials, and labor's first cost. You've seen these numbers before. That's what that maroon is. Then you have simple payback on the right y-axis, and also that's indicated by the green. Finally, the black is the energy savings per year. You'll notice that the dashed line indicates whether or not the technology had a gateway versus a no gateway. The involvement of a gateway is just going to add materials to your project and drive up your cost. So that might be something you might want to consider when you're doing a control system of, if I have a gateway, I will add a fixed cost, so you might need to incorporate more area or think about how you can maximize that. Other things to think about, notice that in the Site 2, it was a very efficient baseline. That's one of the reasons why it is a 45-year payback. So even though it saved 23% energy, saving 23% of 1,000 is still smaller than saving 23% of 10,000. So it's important to know where your baseline is and how effective the different controls can be. The other two sites had much shorter paybacks. They also did have greater energy savings, but the baseline played a role in what their savings were as well. Continuing on for some user feedback, as Gabe mentioned, that was one of the concerns. First column is morning, second column is afternoon, third column is nighttime appearance, feelings about the lighting systems. First row is before system, the fluorescent. The second row is the LED system, obviously. Pretty much the big concern was really in the morning. That might be, and it was both on the fluorescent and the LED. That may not be lighting system dependent. It might be just that we're more sensitive in the morning, or that the daylight is brighter, and therefore, because of the angle of the sun, that might be driving it versus rather what is the lighting system. By afternoon, both systems were pretty acceptable, with no one really complaining. It was either too bright or too dim in either the fluorescent or the LED system. Unfortunately, none of the sites really operated into the evening hours other than Brewery, so we don't really have good comprehensive comparisons to make about the nighttime appearance. And then finally, we asked additional questions about first column being, in this case, satisfied with brightness, either neutral or not. You can see that overall, the fluorescent, they were pretty comfortable with it, yet when they went to the LED system, that resulted in even more satisfaction with the brightness or neutral opinions of the lighting. So that's great to hear. Second column was satisfaction related to automatic control. Again, you'll see that they were somewhat acceptable of the fluorescent controls beforehand, but they were more acceptable of the controls in the post-installation. Finally, the last question was about just the overall lighting conditions, and you can see pretty much similar agreement in both situations. That's probably because finishes weren't changed and other major features weren't changed. Also, most of us on the phone are lighting practitioners or in the field, and we know that you can ask people lots of questions about lighting, and they don't even always sometimes know that you replaced it. So it's not entirely surprising that they like both fluorescent and LED the same. That's pretty expected sometimes. I'll return the presentation back to Gabe.
Okay, thanks, Michael. So we have about 8 minutes left, and I suspect we're going to go a little bit long here, maybe 5 or 10 minutes from our designated hour. So we hope as many of you as possible can hang on until the end. If you're not able to, again, you'll be able to watch a video or a recording of this that we'll be posting to our website. And of course, the report, as well as the 2-page case study documents for each project are also available on the Lighting Controls Case Studies part of the DLC website. So let's talk about lessons learned. As with many projects using new technology and even traditional projects, not everything went smoothly, and we had some things that we learned. The first one we want to talk about is about occupancy sensors. 2 of these projects, as Michael noted, experienced negative savings from occupancy sensors. This means that the energy use actually increased from either the manual controls that existed or the pre-existing occupancy sensors that were installed in some places. As Michael described, part of this had to do with the new operational profiles that are being implemented with advanced sensors and controls. Rather than simply turning off the lights or turning them on based on whether a system senses occupancy, they're doing some pretty advanced things. Some, first dimming the lights after a period of no occupancy, and then after a second delay, then turning off the lights. In some of these cases, some of these systems are doing even more sophisticated things, where they're considering whether adjacent sensors are sensing occupancy and determining whether or not they should turn off or dim and by how much. You can see this illustrated in the graphic on the slide, where with this particular system, which was not one of our demonstration systems, but they've got a great graphic to illustrate this concept, where with this particular system, the lights that are sensing occupancy are at a full 100%, while the farther away you get from where the occupancy is sensed, the dim levels due to no occupancy are decreased. All of this is being done to improve occupant satisfaction with controls. If we save energy with controls, but we distract occupants and reduce productivity, then we may have actually cost our customers more than we have saved them. So to accelerate the adoption of this technology, this is something we need to support. And we need to ensure that the controls are both saving energy and having positive impacts on the building occupants. More on this later in the presentation. And there's no specific lesson learned here other than to say that this is something we need to acknowledge, that new occupancy profiles may increase energy use from prior occupancy sensing methods as we are proposing, considering, and building these projects. Secondly, another occupancy sensor issue here. Thing we learned here is that we really need to consider the occupants' needs and desires for local control. Many of these new integrated sensor technologies, where you've got the sensors integrated into the luminaire, no longer put the sensing or control on the wall. Rather, they are integrated into each luminaire, which provides automatic on control and doesn't require any form of wall-mounted control. Each of these systems does offer optional wall-mounted controls. However, at the time of these projects, they were pretty expensive add-ons, $50 to $100 per switch. If you consider that these optional wireless switches were only controlling a small number of lights, like in a private office or an exam room, they can have significant negative implications for the project paybacks. So we went without the switches in our initial installation to see how the automatic on control would work with occupants. It turned out we had to go back and install these optional switches in a number of spaces on 2 of the projects. In particular, the exam rooms in the medical office building, and also a number of private offices where the occupants wanted the ability to control their own lights, to turn them on when they wanted to, not having them come on automatically, and to dim their lights when they didn't want the full light levels. So the lesson learned here is that we really need to consider those optional switches or other methods to provide to occupants to meet their needs or desires to have local control of their lighting. And we need to work on bringing the cost down of that feature so as to not negatively impact the payback. I think costs are coming down out there for these optional switches, but it's something, I think it's so important for the occupant satisfaction success of these projects that it's something we need to get more ubiquitous and affordable. Next issue was around QA, QC, and compatibility testing. Unfortunately, we had 2 projects here that seemed to install well, only to have some problems occur soon after the installation, which grew worse over time and eventually required the replacement of drivers across the entire project. So this is not a new thing to the lighting industry. Unfortunately, it's a rare thing. But these issues can and do occur on projects. And some of you may recall the first several years or even the first decade of electronic fluorescent ballasts, where occasionally you'd have a problem project like this. And we had one of these, or really 2 of these here on these demonstration projects. In this case, the problems were traced to 2 issues. For one project, there were manufacturing defects in the driver and control connections where the connections worked fine at first, but then they oxidized over time, eventually losing connection. For another project, we had drivers that were substituted to meet the timelines for the project, which is a pretty common thing to do in lighting. However, in this case, the substituted drivers hadn't been fully tested with the new advanced controls, and they contributed electrical noise, which caused problems with the control system. So what can we do about this? Some of this is growing pains with new technology. There's no doubt about that. And we know that the manufacturers of the products that experience these problems in these projects learn from them and immediately implemented changes in their process to ensure these are not going to happen again on any projects going forward. Manufacturers are going to need to continue to learn from these things and improve their QA, QC processes and their compatibility testing. But I think there's a greater role for the industry here, as I think there's a role for industry standards to address some of these challenges. Standards could have been defined, for example, around the electrical noise exhibited by drivers so as to not cause problems with wireless control systems. We know there's a lot of work occurring right now in the industry around standards for these technologies, and there's a lot more work yet to be done. And it's something that we need to continue to support and do more of so as to not inhibit adoption of these technologies due to bad experiences for customers. Third topic for lessons learned is around cost effectiveness. As Michael presented, the paybacks of these projects varied a lot, and they were not great and not in the range that would typically support widespread adoption. And we need to caveat these numbers as we don't believe they were representative of typical projects today. First of all, the projects were 2 to 3 years ago using brand new technology. Second of all, they weren't competitively bid. We chose our contractors and then asked them to price it and move forward. And the contractors also were not generally familiar with the systems, and they needed to include within their pricing time and cost for coming up to speed on how to install and configure the systems, along with just including costs for general unknowns of a new technology. Even so, we know we need to continue to work on the cost barriers with this technology, and we need to better communicate the value proposition of networked or advanced lighting controls. So what are some things we can do here? One finding we did have is that integrated or pre-installed controls, luminaire level lighting controls, can reduce installation labor costs. Installing these controls during the luminaire or lamp manufacturing process can capture economies of scale and efficiencies, and that can be used to reduce the cost of the installation costs of installing these systems. Secondly, there's a role here as well for standards and standardization. Many of these systems continue to be proprietary and as such are manufactured generally in low volumes. We're not able to capture the economies of scale provided by high volume manufacturing. As an example of this, consider the price efficiencies, manufacturers' efficiencies that have been captured incorporating wireless Bluetooth or Wi-Fi communication into everyday devices in our homes and businesses. This is everywhere. Everything's becoming connected, and it's dollars or even pennies to incorporate these communication technologies into devices, and part of what's enabled that has been standardization around the communication and the hardware, around Bluetooth and Wi-Fi. In a similar way, standardizing hardware and communication and lighting systems can help us get to high volume manufacturing, thereby reducing hardware costs. This is something that the industry should continue to consider working towards. If we achieve greater standards and standardization, it also helps us with the other cost effectiveness challenge that drove some of these higher costs, and that it makes it easier to provide education and training for installers. If systems are more standardized in their hardware, how they connect, communicate, and are configured, then we can more easily train the workforce in how to use them, rather than having to train them on individual proprietary systems. We can really scale up that training and education, and with that, we can reduce the installation and cost and time for installing these systems. We acknowledge that this is a really complex issue for industry, standards and standardization, and there's still not a clear standard to support the industry, but hopefully we're moving towards that direction, and it's something that we need to continue to talk about and work on. Finally, around this cost effectiveness, there's a lot we can do to better communicate the benefit of advanced lighting controls and how we sell and consider purchasing the systems. The benefits of these systems go a lot beyond energy savings that they provide. When we have more advanced control of our lighting, we can use it to improve lighting quality for building occupants. With this improved quality, we can improve productivity, employee well-being, and create better environments for our employees and customers that makes them more comfortable in our spaces and want to be in our spaces. In addition, these advanced systems enable smarter management, not just of the lighting system, but of our buildings, our people, and our processes. And this is where the bigger benefit of these systems lies. We spend much of our time building the entire justification for these systems around the energy they save, but the greater benefit is not necessarily with the energy. So a lot of times we reference this 3-30-300 rule when we consider this. And this says that a typical building spends $3 per square foot on energy costs, $30 per square foot on rent, and $300 per square foot on its people. These systems, through their space utilization, benefits and uses, and their lighting quality benefits, they address the much bigger costs for customers in their buildings and people. And but we're not typically considering this in the value proposition for the systems. So this is where we have a lot of work to do in considering and communicating these other benefits of these systems and how we sell and consider purchasing these systems. Our final lesson learned here is around task tuning, also known as high-end trim. LEDs and advanced controls have brought forward a new era of flexible, adjustable lighting. Lighting products are no longer static products with fixed lumen outputs. They're all dimmable and highly controllable. And this presents a large-scale opportunity to tune the lighting to occupant or task needs, saving energy and improving quality of life for people. Several of our projects saved a lot of energy by task tuning. As Michael presented, the largest portion of control savings was actually by task tuning and high-end trim. It was not occupancy, it was not daylight harvesting. But to realize this opportunity at scale, because it's really not part of most projects, we need to make task tuning a standard part of installation of every project. And so here's some things we can do. For manufacturers, one thing you could do is to incorporate this task of configuring your task tuning, your high-end trim, into your configuration apps and software as a standard step. We've seen a lot of these systems with their configuration apps where they kind of walk the contractor step by step through starting up and configuring a space. So if you're not already, build this step into it as a standard step. Contractors, make this a standard part of your installation. After you install the lights and you set up the controls, tune the lighting. And if you don't know what the customer is going to desire, then tune it right to the IES light levels. And so, this, one thing, this is going to require you to have a light meter and also to be knowledgeable around what the IES recommendations are for light levels and what the occupants and tasks will be in the space. But that's I think generally a new practice enabled by LED. For specifiers, procurement, and users, this is something that you can fold into your standard specs to require the contractor or installer to do this step and actually include it in your punch list. So before you leave the job site, this is something that has to be done. And then finally, there's a role for utilities here for supporting this energy saving feature in your programs, considering providing rebates or financial incentives specifically for the implementation of task tuning. We're already providing rebates and incentives for occupancy sensing and daylight harvesting, but as is illustrated by these projects, the task tuning can actually get you more savings. So there's a real opportunity here to develop some specific incentives and program support for this efficiency measure. So lastly, we'd just like to make you aware of where you can find this information on our website. This is a screenshot of the DLC website. You would click on lighting controls at the top, then choose case studies. And here you can see that we've got 5 individual sort of snapshot reports. They're 2 pages long, and then there's a much longer final report that looks across all of the projects holistically, as well as incorporating some of the individual results. So that concludes the webinar today. I want to thank you all for staying on a little bit late here. As we said, we're going to take all the questions that you've submitted, and we will be sending out an email with answers to as many of those as we can. I want to thank PNNL and Michael Meyer for pinch hitting for Eric. And thanks for joining us. I hope you all enjoy the rest of your day.